Welcome to Cars and Aircraft Explained. Modern automotive engineering typically prioritizes a few standard metrics: maximizing straight-line speed, increasing cabin luxury, and integrating complex digital technology. The Toyota Land Cruiser ignores those metrics. It is not designed for peak speed, maximum luxury, or digital complexity. It is built around a central engineering paradox, designed for a far more difficult and absolute objective: to never fail. In engineering, reliability is the hardest problem to solve. Achieving this level of endurance requires rejecting modern optimization trends. Toyota engineers instead utilize a philosophy that prioritizes mechanical survival over a 40-year service life. To understand that philosophy, we have to trace the vehicle's origins back to the 1950s. The Land Cruiser was created as a direct response to harsh military demands, rather than consumer market research. The original project required a machine that could handle extreme terrain, operate with minimal maintenance, and survive long-term physical abuse. The early models were simple, rugged, and entirely mechanical. These rugged physical designs established a baseline philosophy to over-engineer every component. This is a standard Toyota established in the 1950s and never abandoned. While modern manufacturing often relies on planned obsolescence, this foundational philosophy ensures the machine is designed to operate for decades of continuous use. To see how this endurance is achieved, we have to examine the vehicle at the foundational structural level. The vast majority of modern SUVs use unibody construction. Unibody is a technique where the vehicle's structural frame and outer passenger cabin are formed together as a single, continuous piece of metal. Manufacturers prefer unibody frames because they reduce overall weight, cut production costs, and improve passenger ride comfort on paved roads. In comparison, the Land Cruiser utilizes an opposing body-on-frame architecture. A passenger cabin is bolted onto a heavy steel ladder frame. Under heavy downward force, these rigid rails manage load distribution more effectively than a hollow unibody shell. This reveals an intentional engineering trade-off. Toyota sacrifices everyday ride comfort to achieve maximum structural toughness. The separation of the body and the frame provides significant benefits in rough terrain. Because the suspension is mounted directly to the rigid ladder rails, the vehicle gains superior off-road strength and aggressive wheel articulation. In remote environments, modular construction allows for easier field repairs. The body unbolts from the frame, allowing direct mechanical access without requiring specialized workshop equipment. The heavy chassis acts as a resilient skeleton, demonstrating that intentional mass and rigidity will outlast lightweight optimization under heavy physical stress. Moving from the chassis, we reach the thermodynamic core of the vehicle, the engine block. Modern powertrains are usually tuned to extract the maximum possible horsepower from small displacements. Land Cruiser engines operate on the concept of low-stress tuning, or derating. Derating intentionally limits a machine's output so that it continuously operates well below its maximum theoretical failure limits. Left, a standard engine runs hot and vibrates rapidly for peak power. Right, the Land Cruiser engine runs slower and cooler. This strategy allows internal components to operate far below failure thresholds, even after thousands of hours. This low-stress operational baseline also grants the engine a high tolerance for the poor fuel quality often found in remote geographic areas. The result of these restrictive mechanical parameters is an engine block that routinely exceeds 500,000 kilometers of use. Toyota engineers prioritize a predictable, consistent mechanical output over peak performance benchmarks. As the engineers say, this is not about performance, this is about survival. Longevity is a direct result of intentionally limiting power to preserve the physical integrity of the metal. This blueprint of endurance extends from the engine block into the drivetrain and off-road mobility systems. Torque travels through a full-time four-wheel drive system into heavy-duty locking differentials. These mechanical devices force wheels on the same axle to turn equally. Interlocking metal gears ensure forward momentum continues, even if the vehicle loses traction on one side. Housing these massive mechanical systems requires exceptionally high ground clearance and long suspension travel to maintain continuous contact with highly uneven earth. These components align with Toyota's design philosophy, prioritize simple, proven mechanical designs over new, experimental off-road technologies. In hostile environments, technological complexity increases the risk of failure. Every new software system or delicate electronic sensor represents a potential failure point. When operating in total geographic isolation, a software glitch cannot be fixed with a wrench. Physical, mechanical systems are trusted because they are serviceable in the field. Even when modern versions employ advanced systems like crawl control, which modulates throttle and braking, they are built on top of this physical foundation rather than replacing it. Off-road endurance is achieved by minimizing the total number of delicate systems that could fail under pressure. Engineering blueprints are validated through practical testing. The Land Cruiser must prove its durability in the field before reaching production. Toyota engineers systematically apply severe real-world physical forces to the chassis to identify and eliminate potential failure points. Validation protocols require the machine to sustain operation through extreme high temperatures and abrasive dust storms. Desert testing is contrasted with validation in sub-zero freezing climates, forcing the drivetrain to operate in deep snow and ice. This validation process ensures the theoretical over-engineering survives the unpredictable conditions of nature. This rigorous engineering and testing has resulted in a high level of cross-border institutional trust. It is the primary vehicle relied upon by global militaries, remote indigenous communities, and professional explorers. The machine is utilized extensively by humanitarian organizations operating in crisis zones. Medical organizations also use the vehicle to lead convoys across undeveloped mountain infrastructure to deliver supplies. In these volatile regions, the vehicle functions as a survival lifeline rather than a consumer luxury product. Modern iterations have added necessary safety systems and refined interiors, but the core engineering focus remains locked on long-term durability. In an industrial era driven by disposable innovation, engineering a machine designed strictly to endure represents a significant departure from standard manufacturing trends.